The last chapter in Math 60 is going to be chapter 10, and it's about sequences and series. It's a three-part chapter, 10.1, which is an introduction to what a sequences and series is, which is including a bunch of terminology. 10.2, we're going to talk about arithmetic sequences and series, and then 10.3, we'll talk about geometric sequences and series. So the first thing we're going to start off with is some definitions. So the first thing we're going to talk about is a sequence. So a sequence is any set of numbers written in a specific order. And the key thing is that they have to be in an order that you can determine each number in the sequence using an equation. A function whose domain is the set of natural numbers. So anything you put in for n, if you look at this equation here, you're going to assume that n can be any natural number. So that would be any of your counting numbers, 1, 2, 3, and so on. So there's two or three types of sequences. There's a finite sequence where there's an end, and it has a limited number of values because there's an end in the domain that are natural numbers. And then there's an infinite sequence, in which case they go on forever. So like 1, 2, 3, 4, 5, 6, 7, 8, so and so and so and so and so on. Versus finite would be like 1, 2, 3, 4, 5, done. There'd be a finite end. And then the last term is the word alternating, which is when your natural numbers actually will alternate signs. And so you'll go from a +1 to a -2 to a +3 to a -4 to a +5. And when you're coming up with an equation to define each term in a sequence, if it's alternating, you can use this -1 to the n as part of your equation, because when you put in n as any natural number, you start with 1. -1 to the 1 is -1. -1 to the 2 would be +1. -1 to the 3 would be -1. -1 to the 4 would be +1. So it will change going from positive to negative numbers. The next thing is that each of the numbers in a sequence is given the word a term in the sequence. So for example, if you had a sequence defined by this equation, where any term in the sequence can be found by taking 2 and raising it to a natural number. Then your first term would be when that first natural number is a 1. So your first term would be 2 to the 1 or 2. Your second term would be 2 to the 2, which is 4, and your third term would be 2 to the 3, which is 8. So you can find any term in a sequence by putting in the corresponding natural number and figuring out what it would be. So if they ask you to give the first 5 terms in a sequence and the 9th term, and if they first of all asked you to find it when your general term is an equals 2n minus 1, to find the first 5 terms, you do a as 1, except that it defines n has to be greater than or equal to 2. So you're going to find a 2, and you're going to do 2 times 2 minus 1. So the first term would be 3. Your second term would actually be when your natural number is 3, so 2 times 3, which would be 5. Your third term would be 2 times 4 minus 1, which is 7. If you're going to find your next term, 2 times 5 minus 1, which gives you 9. If you were going to find the fifth term, which would be a 6, then it would be 2 times 6 minus 1, which would be 11. So the first 5 terms in your sequence would be 3, 5, 7, 9, and 11. And then if they specifically wanted a 9, then you could plug a 9 in. I've had a lot of debates with myself over the years. I'm like, do they want the 9th term, or do they want one specifically when a is 9? And I looked in the textbook, and this is what they do. So if they say a9, then you're literally just putting 9 into the sequence. You're not finding the 9th term in the sequence. So a9 would be 18 minus 1, which is 17. All right, if they asked you to do it for this one, they're not defining what n is, so n would always start at 1. So you're going to go -1 to the 1, and then 1 squared. So this is just going to alternate the sign for you. So the first one's going to start negative. Negative times 1 squared is -1. And then when you plug in a 2, the 2 is going to make this a positive term, and then it would be 2 squared, so it would be +4. Then you put in 3. This is going to be -9. And kind of when you start seeing the pattern with a sequence, you don't have to plug the numbers in. Like I know it's going squares of numbers so that I know it's going to go 16 and then it's going to go -25, right? I can do it without the equation, but you can always, oops, sorry, I meant to put a 3 there. This would be a 4. I had a pause of thinking. And then we're going to put 4 squared. This would be +16, and then -1 to the 5, and then it's 5 squared, and this would be -25. And then again, if they wanted to find a 9, you would plug in -1 to the 9, so that's going to make it negative, and then it's 9 squared, so it'd be -81. All right, moving on. So the general term. This is a super potentially complicated thing to do in 10.1 because 10.1, the equation can be anything. Just think that coming up in 10.2 and 10.3, you're going to be given an equation to find the general term, but here it's sort of random. You're going to be given a sequence of numbers, and the only thing you know is that you are going to be able to define each term in the sequence using some general equation or to find the general term. So you have to kind of look at it and see if you notice a pattern. There won't be a lot of testing on this. It's not a huge part of the chapter. But it is just sort of kind of interesting to see. So for example, my eyes draw with this one that it goes 4, 16, 64, and 256. And if you know anything about powers of 4, this would be 4 to the 1, 4 to the 2, 4 to the 3, and 4 to the 4. So if I was going to do a general term to find any term in the sequence, I would say that it would be 4 to the n. And that would start with a natural number of 1. So I could go for the 1, for the 2, for the 3, for the 4. They're hit or miss, whether you see them or not. So, you could pause the video now and try the next 2, or you can just be like, okay, I'm going to let Karen do this for me, and then I'll potentially try some in my homework. So I'll go to this one next. You see a 1, and then it goes √2, √3, and then 2, √5, √6. And I can see the pattern, and I don't know whether it's just because I've done this so long, but I can see that if I'm thinking about my n, it goes 1, 2, 3. This would make it 4. And the square root of 4 is 2. So really what it's doing is √1, √2, √3, √4, √5, √6, and so on. And so for this one, the general term would be the square root of n. And again, n has to be a natural number. So I don't have to put any n or whatever it would be. All right, so the next one. This one I see that it's an alternating sequence. So I'm going to go a to the n, and then I'm going to go -1 to the n. So if I put in 1, it'll be a negative term. If I put in 2, it'll be a positive term, and so on and so forth. Then I look at these numbers and I notice that it goes 1, then it goes 3, 9, 27, and 81. And when I see the 3, 9, 27, and 81, I know that between each of these I'm multiplying by 3. So this must be 3 to the 1, this is 3 to the 2, this is 3 to the 3, and this is 3 to the 4. So I can't just do 3 to the n, because if I did that, then I couldn't start my sequence at 3. But if I put 3 to the n minus 1, then when I put in n is 1, I get 3 to the 0, which would give me the 1. And then I would put in 3 to the 2, and then that would give me 3 to the 1, and then I would get the right sign on my thing. So, treat that as you don't have to know that right off the bat, but hopefully when you go to do your homework, maybe you can attempt a few and you see some of the tricks that they sort of will throw at you. So a sequence, again, is just a list of numbers. It's a list of numbers that is not random because it has to be able to be defined by an equation. The difference between a sequence and a series is that a series is the sum of the terms in a sequence. So it's the same. The only thing we do differently is instead of listing them as a number, numbers in a sequence, we write them as a sum or addition, and we call it a series. So just like with a sequence, you can have an infinite series and you can have a finite series. So if you have an infinite series, that means that you're going to go on forever. So to find the sum of these is quite difficult because there's no end. So what we can do is we can find a partial sum. So we can make an infinite series into kind of like a finite series and say, hey, we're going to end it at 4. And then we can say, hey, if there's only 4 terms in the series, that's a total sum. Or we could call it a partial sum because you're finding the sum of the first 4 terms potentially in an infinite series. The notation So when we were talking about a sequence, we were talking about AN, and this represented any term in the sequence. Now when we go to series, we're going to do SN, because series are going to be finding the sum, because they are listed as a plus and a minus, so it's representing a sum. So for example, if I had this sequence, if I wanted to find a sum, it would be -2 plus 4 plus -6, or just -6, plus 8, plus -10, and so on. And so on, because there's a dot, dot, dot. But if I said, hey, I want you to find a partial sum, I want you to find the sum of the first term. Well, the sum of the first term would just be -2, because that is the first term. If you wanted to find the sum of the first 4 terms, it would be -2 plus 4 plus -6 plus 8. And if you added those all together, you would get a sum of 4. So the sum of the, or partial sum of the first 4 terms in the series would be 4. And at this point, there's no way of doing it but adding them together. But again, when we get to 10.2 and 10.3, we'll have equations that we can use. When you're talking about finding sums, mathematicians are lazy, and this is a lot of writing. So for me to say, hey, find the sum of this series and write out the whole series and then tell you what to find the sum of, mathematicians are too lazy. And so what they do is they found a notation. So this is a shorthand for indicating the sum of a series when terms are not known. So you won't have the terms listed out, you'll just have the general equation. So learning a little bit about this notation is that this symbol here, this E looking thing, this is your sigma. And what they're going to do is they're going to show it like this. So they're going to say, this is saying, find the sum of the terms generalized by this equation, starting where k is 1, so this is the first number, all the way up to where k is 4. So that's going to represent the last number. So for this first one, I would, for example, find maybe the first terms. The first term is going to be when k is 1, and it doesn't matter if it's a k or an n or whatever letter you want to use. I find it kind of random. I feel like the textbook starts with an n and then switches to a k, or maybe I started with an n and switched to a k, because it doesn't really matter what letter you use. N makes sense because it's a natural number. But regardless, we're starting for where whatever variables in your equation, it's going to get defined what you're starting at in the bottom. So we're starting at where k is 1. So you get 3. When k is 2, you get 5. When k is 3, you get 7. And when you see the pattern, you don't have to continue, but you can. When k is 4, you get 9. So what we're finding is the sum of the first 4 terms in our series. So if we add those all together, we will get, what, 8 plus 5 is 15, plus 9 is 24. So the sum for that general equation for the first 4 terms would be 24. This next one, they're saying you want to start where k is 0. And so you're not just doing natural numbers, you're starting where k is 0. And so we're going to find when k is 0. So we go -1 to the 0 times 5 to the 0, which is going to be just a 1. And then when k is 1, -1 to the 1 times 5 to the 1, which is -5. And then 2. That's going to make it positive, and then we're squaring it to get positive 25. Then you're doing where k is 3, which is -125. And lastly, when k is 4, this is going to make it positive, and 5 to the 4, which is 625. So we are going to find the sum of the first 5 terms in this series, which is going to be 1 plus -5 plus 25 plus -125 plus 625, which equals 521. Now, the last thing I want to mention before we kind of go on to how to write the sigma notation is just the number of terms. So when we are doing this in 10.2 or 10.3, there's a shortcut formula for finding sum. You don't have to write all the numbers out and add them together. And to be able to do that formula, you have to know how many terms are in the sequence or the series. So what I wanted to show you here is that when you started at k is 1 and went up to k is 4, there's 4 terms because you go from k is 1, 2, 3, and 4. So that's 4 terms. When you started at 0, there was 5 terms. To find the number of terms, you take the top number, the last number that you're going to be finding, you subtract the bottom number, and then you have to add 1. So you get 4 minus 1, that's kind of the difference between, but you have to include that first number. And so this sequence had, or series, had 5 terms in it, whereas this one, 4 minus 1 plus 1, had 4 terms in it. All right, so how do you write sigma notation? Well, you need a formula, and then you need to figure out what you're starting your k value as. So for example, if you look at this one, I'm telling you that this is going to be the formula. So the formula is to find any term in the sequence, you're going to do 2 times k. So what we have to figure out is what we're putting in for k. So you don't have to start at 1. You can start at anything you want. You just define it that way. So that if I wanted to do this one, I'm going to start with a k value of 0 as my first number. And I'm going to go up to a k of, so this is going to be 2 to the 0. I have to figure out what this is going to be. So this is going to be 2 to the 6. So 0, 1, 2, 3, 4, 5, 6. So my last number is going to be 6. So then what you do is you draw your sigma, which is just this and then back into the center, back, out, and up. You're going from where k is 0 up to 6 for the equation 2 to the k. And that is the formula that you would use to then find the sum. So if I wanted to do the next one, this one I'm going to come up with the formula. So I see that it's alternating. So I'm going to do -1, and you can use a k or an n. I don't really care. Let's be consistent. I'll do a k. And then I can see, what is this going to be? So this is 2. And this one isn't powers of 2. Instead, I notice it goes 2, 4, 6, 8. So this would be 2 times 1, for example. This would be 2 times 2. This would be 2 times 3, and so on. So I'm going to say that this is 2k. And it's going to start for where k is 1 and go up to where k is 5, because 5 times 2 would be 10. So my sigma notation would go from where k is 1 up to where k is 5 using the equation -1 to the k times 2k. And again, just plug your numbers into check. Make sure that when you plug in 1, you get -2. Make sure when you plug in 2, you get +4, and so on and so forth. And then this last one, you could pause the video and try this one, or just kind of keep going with it. So I noticed that the exponent stays the same. It's always a 3. It's your base that goes 1, 2, 3, 4, 5, 6, 7. So my formula is going to be k cubed, where my first number is going to be where k is 1. My last number is going to be where k is 7. And this is my sigma notation. K equals 1 up to k equals 7 for the equation k cubed. All right. I was going to pause the video, but I'm noticing there's only one more page for this 10.1, so I think I'll just keep going. If you feel like you need a break or you want to pause, please feel free. But the last part of this is just another type of sequence. So we could have done this kind of more in the sequence section, but I'm just following the pattern that the textbook did. And all it is that in your equation, we did talk about this in one of the ones that we came up with the general term for, but you're going to see this sort of thing happen. So if I went to say, okay, I want to find the first term, I would go a1 equals 3 times a to the 1 minus 1 plus 2, and I wouldn't really know what to do. I'd get 3 times a0 plus 2, but I don't know a0. You have this unknown. So what's going to happen is that they're actually going to give you the first term. They have to, because these are called recursive sequences, where what's going to happen is that every term is dependent on the term before. So you can't do it as we were doing all the other equations. Instead, what we would do is say, okay, I know a1 is 1. So if I wanted to find A2, if I plug the 2 into this formula, all of a sudden I can see that it would be 3 times A1 plus 2. Well, I know A1. A1 is 1. So this would be 3 times 1 plus 2, which would be 9. Then if I go to find A3, it would be 3 times a to the base 3 minus 1 plus 2, which means that it's 3 times the second term plus 2. And then the second term we found was 9. So we're going to plug in the second term being 9 plus 2, which would give me 33. So every term is dependent on the term before. So if I was going to find the fourth term, I would do a to the 4 minus 1 plus 2, which means it's actually 3 times the third term plus 2. The third term was 33. I plug that in. I have 3 times 35, which is 105. And then lastly, to find the fifth term, maybe you've got the pattern. You can see that it's based on the fourth term. Maybe you keep writing this out in whole, sort of wherever you're at. But the fifth term would be the 3 times the fourth term plus 2, which would be 3 times 105 plus 2, which would be 3 times 107, or 321. So recursive term is that every term is dependent on the term previous. Another way of writing this is, instead of going a term is based on the term before with an n and an n minus 1, it can show it like this one. And so it can say, okay, the next term in the sequence is dependent upon the previous term. And instead of doing an n and an n minus 1, they do an n plus 1 and an n. So what that is that when you are finding the first term, it's 0 plus 1. So again, you'd run into this trouble where you'd be like, this isn't going to work because I don't know A0. So then if I plugged in 1, that means I'm actually finding the second term. So if you were to plug in n is 1, you're finding the second term. And the second term would equal 2 times the first term, because n is 1, minus 3. So you would be 2 times 5, because they tell you that the first term is 5, minus 3, which would be 10 minus 3, or 7. So if you wanted to find the second term, or the third term is I guess what we're talking about here, the third term would be 2 plus 1. So this would be the third term. So maybe if I put this in here, it'll make more sense. So you've got your first term, your second term, and the key thing is that your second term is actually 1 plus 1, because n is 1. I don't like this one as much. I don't feel like I'm doing the best job explaining this. But what it is that when you're finding the second term, it's based on the first term. When you're finding the third term, it's based on the second term. And it's because whatever goes in here is 1 more than the n value in here. It's just another way of showing a recursive sequence. So if you're finding the third term, it's 2 times the second term minus 3. So it'd be 2 times 7 minus 3, or 11. If you were going to find the fourth term, that would actually be 3 plus 1. So your n value is actually 3. It would be 2 times the third term, which is 11, minus 3. So 22 minus 3, which is 19. Then if you were going to find the next term, which would be your fifth term, it would be the fourth plus 1. So it would be 2 times the fourth term minus 3, or 2 times 19 minus 3, which is what? 38 minus 3? 35? And so on and so forth. So they're a little bit weird, but the key thing is that one term is always dependent on the term before, and they can show that one of two ways. They can put an n and an n minus 1 like this one did here. So a term is based on the term before, or they can say it like this, where they've got an n plus 1 and an n, so that the next term is dependent on the previous term. And it's just two different ways of writing it. All right, that's 10.1.